Hello everyone, we're Group 12 and our project is die casting process improvement and critical parameter control. Our group members are Abraham Solares, Gustavo Carrillo, Hanming, and Stephen Mansur.
Cast-Rite Corporation is an aluminum die casting facility located in Gardena, California. Currently they're experiencing long changeover times. They believe that they have some opportunities for implementation of process monitoring, and they believe that they have inefficient die storage and retrieval practices that can be improved.
Our project reduced setup time by 86%, increased potential machine availability by 2,800 hours, redesigned a die storage layout and database, designed a custom alignment jig for die installation, identified the benefits for process monitoring, and standardized machine startup by creating new standard operating procedures.
Presentation outline, changeover and setup time reduction, SMED analysis, results, process variable control, statistical process control, die storage layout design, die storage database design. The current problem with changeover and setup at Cast-Rite is that the current changeover is taking 3 hours and 40 minutes. There's one dedicated setup technician, changeover is not continuous from start to finish, and external steps are being done internally. The project was divided into 3 stages: identifying internal and external steps, converting internal steps to external, and improving the setup operation.
On stage 1, we are identifying internal and external steps. During the data collection stage, first we created a flowchart diagram of the setup process. Then, a spaghetti diagram of the setup was made using stopwatches and video recording. Lastly, we interviewed employees to understand the process from their perspective. In order to identify steps between external and internal, we organize it with a table. Individual work elements were consolidated into general tasks. Next, their time was recorded. Then, we identify if the task was an internal or external component. Lastly, the person performing the task was identified.
The current changeover was observed to take 3 hours and 40 minutes. The time spent on each element was graphed in minutes and then identified as an internal or external process. Blue was used for internal and red for external. From the chart, it was confirmed that the die preheating stage requires the greatest amount of time. Here, the work elements have been grouped into internal and external categories. The graph at the bottom of the page displays the machine availability gained by the application of SMED and the overall time saved during a changeover.
The next step of the project is to improve the internal time of the process. We are recommending that Cast-Rite cross-trains the operators to help the dedicated setup technician during changeovers. This will reduce the internal time of the process from 50 minutes to 30 minutes. It will also improve worker utilization by preventing operators from standing idle during changeovers and setups.
We identified 4 key areas for improving the setup process. First is developing a consistent method of die preheating, which is an important factor in part quality. Second is providing assistance to the setup technician through cross-training the machine operator. Third is designing a faster method of mounting and aligning the 2 die halves to the platens of the machine. And lastly is developing standard operating procedures to improve the consistency of the setup process.
Die temperature is a key factor in quality control, but it's also the longest step in the operation. An external die heater will allow the heating of dies to become an external process, and in the process, increase safety by eliminating the use of an open flame and eliminate the cleaning of dies associated with the use of a propane torch. During the mounting of dies, 2 minutes during every changeover are used for alignment, which equates to 32 hours annually. Occasionally, during test runs, the dies require an additional adjustment. A custom jig was designed to eliminate the need for alignment. Multiple size dies can be installed by simply adding the required shims. Cast-Rite has 13 presses available for production, but only 10 of them are involved in the changeover. The cost to manufacture 10 jigs in-house was calculated to be $13,700. This would save the company $8,384 per year in adjustment costs and production downtime.
Pictured here is one of the SOPs that we developed. In total, we made 2 check sheets and 4 SOPs for the setup process. These SOPs cover preheat, setup, cleaning, and inspection of the casting dies and machines. They ensure a smooth die changeover process by separating the process into internal and external steps. These SOPs also follow the same internal format used by Cast-Rite, so they'll be easy to adopt into the regular workflow.
The cost before SMED is how much the company was spending on setups per year. The table shows the cost elements associated with the setup costs. We estimate that the cost of setups per year was about $921,600. The cost after SMED was estimated using the cost elements on the table. The cost per setup in a year is now estimated to be of $141,600. This will save the company $780,000, which will translate into an increase in production capacity per year by increasing production time by almost 3,000 hours in a year.
After analyzing the costs, then we are using analytic hierarchy process to decide which alternative we are recommending to the company. First, we are generating 4 criteria: time saving, labor cost, annual saving, and die heater cost. Then we give our score of all these criteria by how significant each criteria is to the process improvement. The table on the bottom right shows the overall weight of each criteria. Time saving has the highest weight, which means it is the most important criteria. Once it was determined that time saving is the most important criteria, each alternative weight was calculated using the same process as before. The sum product of weight from each alternative and criteria was used to calculate the overall score. The table shows that alternative 4 results with the highest score, which is the alternative we are recommending to the company.
A major source of delays stems from part defects during production. The changeover technician is responsible for the troubleshooting of presses not operating properly. When this occurs, this delays the changeover currently in process. Die casting settings are adjusted only when the press begins to produce parts with defects. The group then decided to investigate which variables are most likely to cause defects in the die casting process. After data collection of the process parameters, a statistical process control analysis was performed.
In order to perform statistical process control, we first collected data using a process monitoring system called Visi-Trak. We then isolated data for variables that would be critical to quality as stated in NADCA literature. We then constructed histograms and I and MR control charts to determine which variables were not in control. The specific variables we decided to look into were die temperature, fast shot velocity, slow shot velocity, intensification pressure, cycle time, and biscuit size.
The histogram is an SPC tool that we are using to analyze the variables. With the data, we are able to see the distribution, as well as the mean, standard deviation, minimum, and maximum value of each data. The next statistical process control tool that we utilize is the individual moving range chart. This chart allows us to identify whether the process is in control or out of control. The individual moving range chart consists of 2 charts: the individual chart shown in the previous slide and the moving range chart shown in this slide. Each chart comes with its set of rules to determine if the process is in or out of control. We replicated this for every variable that we analyzed.
Our analysis has shown that the process is out of control. This leads to production defects which require machine settings to be adjusted. The setup technician is the person in charge of making those adjustments, which are currently based off of feel and experience. By the time the technician is able to make the correct adjustments, an unnecessary number of parts with defects have been produced. We recommend the addition of a Visi-Trak monitoring system to every machine in production. This will provide the ability to use a real-time alert system to warn the operator that the process may be shifting beyond the control limits. The machines and on lights will alert the technician that their attention is required at that particular machine. This will lead to a reduction of defects in parts, which reduces rework. We also recommend that these alerts be investigated to eliminate possible external causes.
Cast-Rite's current die storage method is random. In addition, some dies are stored on the floor between racks, blocking access to some dies. In order to improve their die storage, we used a warehouse storage layout algorithm which scores each storage location based on its distance in feet from the entrance of the storage area and pairs the closest locations with the most accessed dies. For safety, we are recommending they only store their largest dies at ground level. In addition, we believe they could greatly benefit from a database that will be used to search for dies. Here we have our first alternative for the storage layout. This alternative does not account for any potential difficulties or safety concerns with retrieving dies from higher shelves. This alternative groups the most frequently used dies at the locations closest to the aisle. In alternative 2, we weighed vertical distances as 10 times greater than horizontal movements. This groups frequently used dies closer to the ground, allowing for easier and safer retrieval of frequently used dies. However, commonly used dies will also be stored further back on the racks.
It was observed that locating die was done by memory from one of the two-room technicians. We created a custom storage database which would accurately return the location of the casting die. Anyone involved in retrieval of die can simply input either the die's part number, the part serial number, or the internal storage number into the database, and view the die location from the output as shown in the table. The walking distance during changeover was observed and recorded with the use of spaghetti diagram. This shows the routes the technician takes when performing a setup. Then, the traveling distance was obtained using a Form-2 chart as shown in the slides. The chart shows that the current changeover procedure requires a total walking distance of 1,918 feet. In order to eliminate the waste of movement during the setup process, we suggest moving the tooling table and piston head storage to the open space in the upper left corner in the facility, with the recommendation to use a die heater to preheat dies. We generated two heater location alternatives. The first alternative is to place all 4 oil heaters in one location near the staging area for changeover. And the second alternative is to place heaters throughout the facility as shown in the diagram on the right. The group decided on alternative 1. Space is limited next to the presses, and placing die heater next to the machine may cause a safety hazard to the operator. We then use spaghetti diagram to show the improvement of the setup. With this layout, the total distance now traveled during a changeover has been reduced to 908 feet, which is an improvement of 52.7% in distance traveled.
The overall project economical analysis is based on the fact that Cast-Rite would need to invest $56,000. This would include buying the industrial oil heaters, cross-training operators, manufacturing the jig in-house, and fixing die cooling lines. We're projecting that they save $780,000 a year for the next 5 years. Again, we want to say that this translates into an increase in production capacity by increasing machine availability by almost 3,000 hours a year. The present value of this project is worth $2.5 million.
In conclusion, we recommend Cast-Rite adopt SMED principles into their setup process. Cross-training operators to assist in setup will allow them to reach that goal with minimal cost. Implementing oil heaters for an external die preheat is the most important step they can take to implementing SMED. Using an alignment jig will improve consistency in die mounting. We recommend that Cast-Rite implement a process monitor to all of their machines simultaneously in order to maintain process control. Restructuring their die storage layout will allow them to retrieve dies more reliably and quickly. Using and maintaining a database will allow any employee to locate dies easily. Lastly, creating a single die staging and preheating area will reduce wasted time and movement of those involved in the setup process. With these recommendations, we believe that Cast-Rite can greatly improve the speed and reliability of their setup process and operations.